Okay. All right. Well, happy Friday, everybody. And can you believe it? Next week is week 5, and then it'll be November, on Thursday. It seems a little crazy. Anybody doing anything for Halloween? Anyone getting dressed up?
Skip the class.
We're not gonna skip class. We're gonna have a very exciting class on Halloween. So you guys better come. All right. Actually, I don't know. All right. Okay, but all right. We're doing Bayesian stuff now, right? Bayesian statistics. We're on week 4 Friday. Okay. So let me just kind of recap the past few days on. All right. Shh. Okay. Settle down. Okay. So 1 week ago, I kind of contrasted kind of Bayesian thinking with classical statistics, frequentist thinking, okay? In frequentist, you just kind of take the data that you get, you form a maximum likelihood estimate, and you go with that, okay? And then on Wednesday, we saw that in Bayesian statistics, we do not model our parameters as fixed values, but rather with an entire distribution. Okay, so on Wednesday, I said in classical statistics, you would just use the maximum likelihood estimate of something like 0.6 if that's what you drew out of the bag. If you drew out of the bag 6 red and 4 blue, your MLE estimate would be 0.6, and that's what you would go with. In Bayesian statistics, we said the proportion that's red is modeled by a random variable. And so that value can be anything from 0.1 to 0.9 if there's 10 marbles in the bag, or if we don't know how many marbles that are in the bag, it's going to be modeled by a beta distribution, right? That goes anywhere from 0 to 1. And then after seeing your data, we said you would update the distribution for what you believe P is. And the distribution you get after updating from seeing your data is known as the posterior, okay? The posterior distribution in this case would say that values of like 0.6 is most likely. Values like 0.5 or 0.7, those are still very likely, but values like 0.1 and 0.2 are unlikely, okay? Even though they're unlikely, they are still possible. And therefore, when you are going to make a prediction about what could happen in the future or ask a probability question, you have to consider every single possible value of P, okay? Does this form look familiar? Like if you had to do this integral, where P is a continuous distribution. So rather than doing the summation against all 9 possible values of P, now you have infinitely many possible values of P. Does this form look familiar? No? Yes? It's if we move the f of P, which is a PDF, right, to the other side, then it becomes like Monte Carlo integration or Monte Carlo estimation, right? This function over here that we're trying to calculate based on P is your h of x, or in this case, h of P, and then you have an f of x or f of P. That's a PDF, okay? And so Monte Carlo methods work very well because if we wanted to get this calculation, this is a tough integral, or it could be a tough integral to calculate, but with Monte Carlo integration, Monte Carlo estimation, our work is a lot easier, right? We just generate values from that thing. Okay, and then we introduced this beta binomial distribution, and it only just got as far as talking about what the beta distribution is. Okay, so today I want to continue talking about the beta binomial, all right? Continue the beta binomial model, and specifically, I want to talk about how we are going to update our beliefs about P after viewing our data, okay? And so let's just review. Bayes rule. Okay. So what is Bayes rule? It's the probability of B given A is equal to, do you guys remember? Probability A given B multiplied by the probability of B divided by the probability of A. Okay, all right. Some of you guys are like whispering it, but yeah. So that's Bayes' rule. Okay, this is what it looks like in Bayesian statistics. Okay, replace B with the parameter. Okay, so for the beta binomial model, the parameter that we're trying to estimate is the proportion P. Okay. Is the proportion or probability of success P. And then replace A with the data. Okay, and so this becomes and kind of the generic. We'll say the parameter, we might just write theta, and the data will be D. Okay, so we'll say the probability of theta given the data. So this is known as the probability distribution I'm just going to write it out. Okay, the probability distribution representing our beliefs about the parameter theta given or after we have seen the data D. Okay, this is called the posterior distribution. Posterior distribution, and I guess its full name would be of theta given data. Okay, the posterior distribution. Okay, so this would be the probability of theta given data is equal to, and then using Bayes' rule, it would be D given theta times probability of theta divided by probability of data. Okay, so I'm just using Bayes' rule, and I'm just replacing the A's with the D's and the B's with the thetas or whatever. Okay, we're just doing some letter swapping here. And I said probability of theta given data is the posterior distribution, and it's the probability distribution representing our beliefs about the parameter theta after we have seen the data D, and that's why we call it the posterior. Okay, so let me just kind of break down each of these components. Okay. Probability of data given theta. This is the probability, or actually probability, but we call it the likelihood of getting our specific data set D, okay, if the parameter value of theta is theta, okay? Okay, maybe I'll just write it. It's the probability of getting our specific data set D for a given value of theta. Okay? And so probability of d given theta is a function of theta. Okay, the probability of d given theta is a function of theta. Okay, you plug in a different value of theta and you will get a different value of this probability. Okay, so you probability of data is a function of theta. Okay, the data d is a fixed set, basically equal set to what you have observed. So you don't have the power to change what you've observed. What you've observed is what you've observed. And it's a function of theta, okay? If that parameter that we're trying to figure out changes, how would that affect the probability of my data here, right? So let's say you've observed two heads, right? You flipped the coin twice and you got two heads, okay? So now the question is, what's the probability of getting two heads for a different value of theta? If we say, what if theta was 0.5, the probability of flipping heads is 0.5, then the probability of getting your data would be 0.5 squared, 0.25, okay? If the probability of flipping heads was 0.7, then the probability of your data would be 0.7 squared, 0.49, okay? So it's a function. The probability of data given theta is a function of theta because your data is fixed. The probability of theta, this is, okay, so this is called the likelihood. And this one's called the prior. Okay, this is the distribution representing our beliefs of theta prior to looking at the data. Okay, and this is maybe people's objections to Bayesian statistics. This is subjective to, I guess, subjective to the person setting it up. Okay, it's usually based on historic data, but my experience in life is different from your experience in life, and so we might observe the same. We might both watch a video, right? And we can walk away with different opinions because my life experience is different from yours. So our prior beliefs are different. But we have some general consensus ideas of what to do for our prior beliefs. Okay. All right. And then lastly, probability of data. This is called the marginal probability. Okay. This is a constant. Okay. This is an important thing. It's not a function. It's a constant because it depends only on D, which is a fixed data set. Okay, and this represents the probability of getting our data D our exact data D if we consider every possible value of theta. Okay. What is the probability that I get two heads in a row? Okay, if I consider every single possible value of theta. If I considered it for theta equaling 0.5, if I considered it for theta equaling 0.51, if I considered it for theta equal 0.52, what's the probability of getting D for every single possible value of theta? All right, so those are the different pieces, and so I guess just get used to hearing these terms, okay? We have the posterior, the likelihood, the prior, and the marginal, okay? These are the key terms that exist in Bayesian statistics. Okay, so let's, all right, and yeah, this is a constant. Often the constant is difficult to calculate. Okay, but why do we even, if the constant's difficult to calculate, and if it's only a constant, why do we even bother trying to calculate it? Yeah.
You need the probability to be out of line.
Exactly, right? This thing, this posterior distribution, probability of theta given data, it is a PDF. It is a probability distribution. And the number one rule for PDFs, there's two rules, okay? And you cannot violate them if you want a PDF. One, every value has to be positive. You can't have any negative values in a PDF. And number two, the PDF must integrate or add up to 1, okay? And if it doesn't, it's not a PDF, right? And we docked heavily, well, not super heavily, but we docked a significant number of points on the midterm if your PDF or CDF doesn't integrate to 1. That's a key thing, and that's why we have to calculate this constant in order so that the resulting PDF integrates to 1. Okay, it is necessary. So the PDF P of theta given data integrates to 1. Okay. Yes, our life would be much easier if we didn't have to calculate this. Okay. I don't know about life, but this step would be easier if we didn't have to bother calculating this. Okay. Life can be hard no matter what you do. Okay, but here we are. All right, let's go. So we'll go back to the beta binomial model. Okay. Okay. So our parameter is theta. Okay, and the data we observe comes from a binomial distribution. Okay, so let's say we observe 6 red marbles out of 10 draws. Okay. So we're still dealing with our bag. Okay, and we don't know how many are red. So we did 10 draws with replacement. We get 6 marbles. Oh, okay, and just for the sake, unknown number of marbles, unknown proportion red. Okay, so we'll just an unknown proportion, but we're only just trying to get the proportion red. Okay, so we observe 6 red marbles out of 10 draws, and so the likelihood is going to be from the binomial model, and it's n is equal to 10, x is equal to 6, and p is unknown. So this is going to be 10 choose 6 p raised to the 6 times 1 minus p raised to the 4. Is that okay? So I'm going to just write the probability of, is this theta given our data or data given our theta? This is going to be the probability of our data given a value of p is proportional to p to the 6th times 1 minus p to the 4th. Okay? Or, I mean, I guess I'll say it's equal to 10 to 6. All right, so this is our likelihood. All right, prior distribution. The prior distribution, we will use a beta distribution, okay? Okay. The reason why is, well, I guess you'll see later, but basically the beta distribution is known as the conjugate prior to the binomial distribution. Okay, what does that even mean, right? I don't know, what is exactly is the definition of conjugate? I think it means that they go well. I don't know. What define conjugate? And maybe we'll find something we didn't want to find out. Okay, but all right. I'm going to close this. Or wait, did everyone respond to the attendance poll? This is hard to read. Okay, give the different forms. Oh, no, that's like to conjugate. You know, soy, s, somos. Okay, that's my knowledge. All right. Okay, coupled, connected to, or related in particular, right? Okay, so that's what we want, right? This is the prior distribution that is coupled with the binomial distribution. Basically, what it means is that there are nice mathematical properties, okay? Nice math properties that allow us to multiply the two together. Okay. So if you use a conjugate prior, when you multiply them, the terms combine nicely. That's basically all it says. Okay. So the beta distribution has PDF equal to, here, let's go to Wikipedia and look up the beta distribution. Okay, and it looks like this. X to the alpha minus 1 times 1 minus x to the beta minus 1 divided by beta, alpha, beta, where beta, alpha, beta is gamma, alpha, gamma, beta divided by gamma, alpha, beta. Okay, alpha plus beta. All right, no big deal. All right, this is in the denominator, so what I'm going to do is I'm going to flip this, okay, and put this up here, right? So I'm going to do gamma alpha plus beta divided by gamma alpha times gamma beta times, and then we're going to do the PDF of P, right? It's the distribution of P, so it's going to be P to the alpha minus 1 times 1 minus P to the beta minus 1, okay? So all I did was I just replaced the X with P, okay? And then I just, because this is in the denominator, I flipped this and I put it up here. Okay, so the beta distribution has this, this form. Is that okay? All right, this looks scary, right? Like the gamma function's this scary looking thing. It's actually not, but it is. It feels scary, okay? The gamma function is basically, you guys understand factorials, right? Like if I say, what's 3 factorial? You do 3 times 2 times 1 and you get 6. And what's 4 factorial? You do 4 times 3 times 2 times 1 and you get 24. And 5 factorial becomes 120, right? So the gamma function, it's what if we connected the dots, right? So that you, instead of having, you know, where it's only defined at 3 is 6 and 4 is 24 and 5 is 120. What if we had like a smooth line that connects them? And then that's the gamma function. Okay, so the gamma function just is basically the factorial function, but it's smoothed out. And then they shifted it over by 1 for, you know, whatever reason. It looks crazy on the negative side because if you think about factorials with negative numbers, like the odd ones will be negative and the even ones will be positive. So the gamma function looks totally scary on the negative side. But don't worry, okay? Just think of the positive side, as you always should, and it's just a smooth function connecting the dots on the factorial, okay? But you don't even have to worry about that, right? Because all this boils down to, this is just a scary constant, okay? That's all it is, okay? This serves, its only purpose is so the PDF integrates to 1. Okay. But yeah, you know, I don't know, the gamma function, it looks, it's a little, I mean, the math behind it is weird, but conceptually, it's just connect the dots for the factorial, okay? But it's just a PDF, just a constant, so the thing integrates to 1. You don't have to worry about it. The only thing that really matters is this p to the alpha minus 1 and 1 minus p to the beta minus 1, okay? So prior to looking at our data, maybe our prior beliefs, we're going to use just a flat prior, okay? So we will use a flat uninformative prior. This just means before we look into our bag, we're open to the possibility that the proportion read is anything from 0% to 100%, okay? Because we don't actually know. Somebody says there's some red marbles in this bag. It's a secret, I'm not telling you, okay? So you're saying, okay, before looking at the bag, looking into bag, we will consider any value between 0 and 1 for A. Between 0 and 1 for P as equally likely. Okay, so that is going to be, probability of P is going to be a beta 1, 1. So this is going to be constant times P to the alpha minus 1 times 1 minus P to the beta minus 1, okay? And so this just becomes some constant times P to the 0 and 1 minus P to the 0. And so we just get a constant 1, okay? But I could just leave it as this, all right? Okay, let me, and then probability of D, this is just going to be a scary constant. A scary to calculate constant, I should say. Constants aren't scary, but it's a scary to calculate constant. Okay, so we've got, we still want the probability of P given our data being 6 red out of 10 is equal to the probability of our data given P times the prior, the probability of P, divided by the probability of D, okay? All I'm going to do is I'm going to just say this is proportional to, and this just allows me to combine all the constants together in some unknown constant, right? So this probability of D given P is going to be P to the 6, 1 minus P to the 4. And then the probability of P was some constant, but we said it's going to be P to the alpha minus 1 times 1 minus P to the beta minus 1. We happen to use alpha as 1 and beta as 1, so it ends up being 1, okay? And then because probability of D is a constant, we also don't even have to worry about it, right? Is that okay? All right, and so so this being the binomial likelihood and this being the beta prior, these combine nicely, and we have P to the alpha minus 1 plus 6, and we have 1 minus P to the beta minus 1 plus 4. Okay? And then there's got to be some kind of multiplied by some constant so that the thing integrates to 1. Okay. Well, is this in the form of a PDF that we know? Okay. It is in the form of a beta PDF, which is in the form of constant of P raised to basically, I'm going to call this shape 1 minus 1 and 1 minus P to the shape 2 minus 1. Okay. Okay. And so the probability of P given our data is if we let shape 1 equal alpha plus 6 and let shape 2 equals beta plus 4, we have the probability of shape 1 minus 1 times 1 minus P to the shape 2 minus 1, right? And so this just means probability of P given D is going to be a beta distribution with shape parameter alpha plus 6 and beta plus 4. Okay, and if the prior has beta 1, 1, then the result where alpha is equal to 1 and beta is equal to 1, then the posterior is probability of P given D is the beta distribution of 7, 5. Did this feel like black magic, or is this okay? So this is why it's the conjugate prior, the beta and the binomial. Okay, the binomial distribution has this PDF, right, or this shape parameter, and because the beta distribution is defined kind of using similar terms, when we combine the two, we end up getting something still in the form of a beta distribution, okay? And all of those crazy terms, you know, the 10 choose 6, and then the gamma alpha plus beta and all of that stuff, and then even the entire constant that was in the denominator, probability of data on the bottom, we're just going to combine them all into some unknown mystery constant that we're not going to worry about for now, and we're just going to say, you know, if we get it in the form of a PDF, then, you know, then it's going to work because the PDF has to integrate to 1, right? And so that constants, whatever they were, we don't even care anymore. They all just combined, and we're just going to say, okay, this had to have worked out somehow. Okay, we know if we use beta 7.5, that's going to integrate to 1. Okay, so that is that's our first thing, right? So our posterior distribution. So after seeing 6 red out of 10 draws, our posterior distribution is beta 7,5, okay? And let's just take a look at what beta 7,5 looks like. All right, so S is going to be a sequence. This is so exciting. I don't even have to like resize my window because it fits on the whole screen now. All right, anyway. S d beta, so we want 7,5 type equals L. All right, let's plot this. Boom, okay. There you go, all right? And what we see is that the maximum value is at 0.6, okay? Which makes sense, right? We saw 6 red out of 10, so our maximum value, but this is now considered, this is the most probable value of P based on our data, okay? All right, does this feel okay? So now we have a distribution. P is not a single value. This is probably the biggest shift that you have to get over. P is not a single value, but it's described by a distribution. And right now, let me copy this. Okay, let's copy that. Oh, I should have said X label is P. Okay, so that's what we want. We're going to export this, copy to clipboard, copy this plot. Let's throw it in our thing here. So this is our posterior distribution of P. So P is not a single value, but represented by a distribution. Okay, let's talk about further updating. Okay, let's say we gather more data now. All right, so let's say I'm going to go to the bag. There's some marbles in here. We're going to draw some out, okay? All right, let's say I draw, I don't know. How many marbles should I draw? Okay, that sounds good, 42. All right. And how many do we get that are red? We draw 42 marbles with replacement. How many are red? Just 43? I can't get 43 red marbles if I only drew 42. All right, try again. Wait, how many, just throw out a number.
30.
30. Okay, so we're gonna get 30 red marbles out of 43. Okay, so we get 43 draws, okay, and then 30 are red. Okay, so what's 30 divided by 43? Okay, so, almost 70% are red, okay? Let's, how should we go about doing this, okay? So now, I have already seen some data, okay? So, prior to drawing my 43 new marbles, what are my beliefs about P? it's this, okay? It's this. This represents my beliefs now prior to getting, drawing 43 more marbles, right? Okay, so now, prior to drawing 43 marbles, my beliefs about P are represented by beta 7, 5, okay? Which has a max value at P equal to 0.6, okay? And then, okay, so, and then now my data is 30 red out of 43 draws, okay? And so my likelihood is going to be equal to, you know, some 43, choose 30, it doesn't matter. P to the 30th and 1 minus P to the 13th, right? Okay, and the prior is equal to, you know, some constant times P to the 7 minus 1 and 1 minus P to the 5 minus 1. Okay, and then the marginal is just going to be some crazy constant. Okay, so the posterior probability of theta given our data, or P given our data, is going to be the likelihood times the prior divided by the marginal. And that's just going to be proportional to P raised to the 30th, 1 minus P raised to the 13th, times, and then again, because I'm just doing proportional, it's going to be P raised to the 7 minus 1 and P raised to the 5 minus 1.
1 minus P?
Oh, I'm sorry, 1 minus P, thank you. Okay, 1 minus P to the 5 minus 1, exactly. Okay, and then so we get, this has got to be proportional to P to the, I don't know, 36, and 1 minus P to the 17. Is that right? Did I add correctly? Okay, good. All right. And we say, all right, a beta distribution has the form P to the alpha minus 1 and 1 minus P to the beta minus 1, okay? So our posterior is going to be beta with, what's our alpha? What's that? 37, and what's our beta? 18, okay? Good. Let me just show you what this kind of looks like, all right? So I'm going to do 37, and what was the other one? 18? 37 and 18? Yeah, all right. Okay, so after updating, right, after observing 42 more values, okay, this is my beliefs about P. Now I'm a lot more confident that it's somewhere around 0.7-ish, 0.68-ish or something, okay? And in fact, let me just add d beta all right, I guess 31 and 14. All right, let me just show you guys this. All right, yeah, I'm still talking. All right, whatever. this red line represents what we saw prior, okay? This was prior to observing our 42 draws, okay? We said 0.6 was the most likely value, okay? If we looked at the likelihood of the direct data itself, which was 42 draws, it had an average somewhere around 0.7, and that's what this blue line represents. When you combine the two, it picks a compromise between the two, giving, more weight to whichever one is, more pointier, okay? And when you combine the two, you get like a hybrid between what you believed prior, what your data says, and this ends up being your posterior distribution. Okay, anyway, thanks for sticking around and not being rude to you guys. No thanks to everybody else, but have a great weekend. We'll see you guys on Monday.